I was actually, I was asked yesterday to give some explanation of this, so let me just quickly start with that. So remember, d of t was the total variation distance maximized over the starting point of the distribution at time t minus the stationary distribution. Now, suppose we take an eigenfunction. So Pf is lambda f. This is just the right eigenvector for the transition matrix. And let's normalize it so that its maximum norm, I'll write infinity norm, is 1. In fact, let's take the maximum of f itself to be 1. So if we need to, we are going to normalize f and flip its sign, so we can certainly ensure that f will satisfy that. And okay, and then if you look at p to the tf, I claim that just because the norm of f, well, norm of p to the tf we can, on the one hand, compute because it's an eigenfunction. So this is just going to be the infinity norm. P to tf is just going to be lambda to the t in absolute value. But on the other hand, this is less than twice d of t. So, and the reason for that is just the definition of the total variation norm as half the L1 norm. So if I take if I look at p to the tf, and I want to, at some point, call this, at some point z. So this is by definition, it's a sum. It's this sum. So if I want to compute that L infinity, I want to compute this. I'm sorry. If I want to compute the L infinity norm of this, I will have to just maximize this over the choice of z. So yes.
Possibly your microphone is
not working. No.
Sometimes
Okay, I'll try to just speak louder, but okay. Now, something that came up in one of the actually short talks yesterday is that we always have that if f is such an eigenfunction, and I'm going to take lambda different from 1, then f is going to be orthogonal to pi. So if you take a sum of f of w, pi of w, this is always 0. Okay, good. So in the reversible case, this is just the fact that this is the fact that eigenfunctions with respect to different eigenvalues are always orthogonal, but this in fact is true even in the non-reversible case. Anyway, so using that, we can just rewrite this as the sum of pt zy minus pi y times f of y summed over y. And okay, and now we can just take absolute values. This is, so these quantities are positive, but this will be meaningful here. And then we get that this is, remembering that we've taken the f to have norm 1 and the maximum n infinity norm 1. So this is less than the sum pt zy minus pi of y. Okay, which is the total variation, which is the L1 distance between pt and pi. So because if we take now z, which is, so take z that maximizes this, and you'll get the statement we want, because then this will be, if you take the z that maximizes, this will just be 2 d of t for this choice of z.
So,
Yes.
do you want f to be a left eigenvector? Because pi
F-
is a left eigenvector.
You want the right one.
You want f to be a right eigenvector. So when we say f and 1, so this orthogonality, f is a right eigenvector, and this is not orthogonality of f and pi, this is orthogonality of f and 1 in L2 of pi. Okay? But, so f is a right eigenvector here. Okay, but this you can just verify directly. So, in fact, it may be clearer if I write it in the other order. That's now it should be obvious. Before it was tricky, but now it's obvious. Okay, so right. So just remember that you do this by writing some. You do with. You compute pi times p times f in 2 ways. So on the one hand, pi is a left eigenvector, so this gives you this gives you pi times f, and on the other hand, f is a right eigenvector, so this gives you pi times lambda f. So again, pi is a left row eigenvector, f is a right column eigenvector, and P is the transition matrix. So just comparing, right? And this is a scalar product of a row vector with a column vector. So just comparing these, you get the statement. Okay. So once you take the z that maximizes this, you will get a statement. So you have lambda to the t is less than 2 d of t. Now if you apply this with t, which is the mixing time, t mix of epsilon, then then what you get is that lambda to the t is going to be less than 2 epsilon. Okay, so t times the log of 1, so take 1 over and take log, so it's bigger than the log of 1 over 2 epsilon. But this is less than t times 1 over lambda minus 1. Okay, and from here to here, it is one more step of algebra that I will leave to you. So So this will easily give you the left inequality. As for the right one, one way to think about it is to compare L1 and L2 norms. So if you start with the delta x, so a unit vector at x, I want to think of that as a measure. So let's take that as a row vector. So this is just a measure that's concentrated at x. And you can write it as a combination of the left eigenvectors. So it's some combination, maybe sum of aj phi j, where these are the left eigenvectors. So phi j times p is lambda j phi j, and in particular lambda 1 equals 1, and the corresponding eigenvector is just pi, so pi times p is pi. But now you take this identity and you apply p to the t to both sides. So delta x p to the t equals the sum aj lambda sum over j lambda j to the t phi j. So right, so the point is when you apply p to the t to phi j, you have, right, we're just using this identity in the tth power. And now just take L2 norms of both sides and use the, so this I'm doing just in the, so maybe this is not stressed enough. Yeah, this inequality on the right is only in the reversible case. So I should stress that. So this is, we're looking now at reversible chains. Okay, and now if you compute L2 norms of both sides and use orthogonality of the eigenvectors, you'll get that the, so what I want to take is delta x p to the t and compare its distance to pi in L2. So, but I want to do that in the right normalization. So we take delta x p to the t, this is some measure. We're going to take its density. So its density with respect to pi. So this maybe at y divided by pi of y, into subtract 1 and compute the L2 norm in L2 of pi. Where y is the variable. Okay, so let's compute this L2 norm squared. So the phi j are orthogonal in L2 of pi. That is the key thing here. So let's see. So we may want to write this expression. So when I take, so actually, let me change this a little bit. The function I want to expand in L2 is actually going to be delta. Yes, I'm trying to explain the second inequality. Yes, which. Something. Oh. So in fact, it's best, let me change this a little bit. It's best to do this expanding, not delta x. This is why sometimes it's convenient to take pi uniform. Otherwise, we always have to normalize with the pi. So actually, what will be convenient is to expand not delta x itself, but so at least I want to explain it with the density function, delta x over pi. So we're going to expand this density function as, so this is going to be a little bit, let me change this a little bit. With so actually now we'll take the phi j to be the right eigenvector. That's actually the best way. Then so let me write this more carefully for you next time. I'll just say this. Sorry. So the idea, which is very simple, is you take the measure delta x, you expand it, or you expand the density in L2, and you look at the effect of multiplying by the high power of the operator. And you see that in L2 norm, you contract by a factor of which is better than lambda 2 to the t. So the distance, but the distance of the density to, or the measure to the stationary distribution will shrink by a factor of lambda 2 every time at least. So because the eigenvalues, all the ones besides 1 are all at most lambda 2. I'll write this for you in detail later. I was confusing the left and the right eigenvectors. So let me come back to this point and just all right. So I'll come back to this right-hand inequality. Okay. So one topic which often the graphs we're interested in are bipartite graphs. So in a bipartite graph, the random walk doesn't mix because at any time you are either on the left side or on the right side of the graph. So a standard remedy to this is if we have a bipartite graph, we look at the corresponding lazy chain. And this is often convenient even if the graph is not exactly bipartite. So for any chain, we can make it lazy by making the simple change, averaging P with the identity matrix. So this corresponds to, at every step, instead of moving with the chain, we toss a fair coin. If it lands heads, the chain, we take a step. If it lands tails, we just stay where we are. So that's a lazy chain that corresponds to a given chain. And such a lazy chain always has the property that Pxx is greater or equal to half. So that's our formal definition. A chain is lazy if Pxx is at least a half. Now, when you do this kind of averaging, so you start with any chain and average P with the identity, of course, all the eigenvalues will be also averaged with 1. So all the eigenvalues will be in the interval 0, 1 instead of in the interval -1, 1. And positive eigenvalues are also convenient to work with. So some examples that we'll see in some more detail are lazy random walk on a cycle and lazy random walk on a hypercube. In both these cases, one can compute explicitly all the eigenvalues and eigenfunctions and use that to get an exact spectral decomposition of the walk. So one thing you get from, let's see, so a useful formula you get from the spectral theorem is if I look at PTXY, divide by pi of y, this is equal to the sum over j, lambda j to the t. Now I'll call them fj, fjx, fjy. So, and here fj are the right eigenvalues, so p of j is lambda j. Fj, and the fj now are normalized in L2. Okay, and again, you can find this in the beginning of chapter 12 of my book with Levin and Wilmer, or in many other places, or just see it as an exercise in diagonalizing matrices. So because of this, if you know all the eigenvalues and eigenfunctions explicitly, you can compute everything you want about the chain. But the chains where you have such knowledge are quite special. So we'll want to have more robust techniques that can be used in settings where you can't compute exactly all the eigenvalues and eigenfunctions. Okay. Now, one difference is in the cycle, it turns out the relaxation time and the mixing time are both order n squared. So while on the hypercube, they're different. We'll see the significance of that soon. Okay. Now, besides explicit calculation with eigenvalues and eigenfunctions, another technique that certainly probabilists like a lot is the method of coupling. So in general, a coupling is just a joint distribution on two Markov chains, or two random variables, if you want, more generally. So we're going to have two Markov chains, xn and yn. And in the coupling, when you look at xn separately, it follows the law of the given Markov chain. The same for yn. They typically have different starting points. And the goal will be to define really a Markov chain on pairs, where when we look just at the x-coordinate, we'll get xn. When we look just at the y-coordinate, we'll get yn. But we want the two paths, even though they start at different points, to meet and continue together. So we'll see this in some example. So let's take the lazy random walk on the n cycle. So again, the chain stays in place with probability half. With probability quarter moves right, a quarter moves left. Now suppose I start two copies of the chain at 2 points x and y. We're going to couple them as follows. We're not going to run them independently. We flip a fair coin to decide if the x particle or the y particle moves. And so if the x particle is moving, then it's going to move with probability half left and half right. And similarly with the y. So with this rule, the movement is no longer independent, because in fact, only one of the particles will change location. But if we look at each of them, if we look just at the x particle, what's happening to it? Well, with probability half, it's staying in place. And with probability half, it's moving. And in that case, it's equally likely. So it's behaving correctly according to our lazy Markov chain. And the same for the y particle. But so both of them perform a lazy walk. Now, we're going to change the rule once they land in the same position. So one of them, they're never moving together. So one falls on top of the other. Then we will continue them together. So you can easily see that with this rule, we still maintain the fact that that both x and y are copies of our original Markov chain. Now this, it's very intuitive, but one kind of warning is a standard place of mistakes in papers is people assert the following is a coupling and they don't check it. So this is couplings are very intuitive, but they also have some pitfalls. So really, that is a point to really carefully check that when you have a coupling, indeed each of the coordinates behave according to the prescribed rule. Yes.
The coupling time have a geometric tail.
Have a?
Geometric tail in this particular coupling that you are supposing.
Well, it's not exactly geometric, but in
Dominated.
it's dominated by some geometric, but the parameter of this geometric can be large. So so as the cycle grows, the parameter of this geometric grows. So it's not right. And since we want, there's a classical, besides the classical theory of Markov chains, there is a theory of chains on general state spaces. And often in that theory, you'll see statements like geometric ergodicity. You should be aware of such statements. Often they are meaningless because a statement like that without exact control of what is the parameter in the geometric ergodicity is often useless, although it is, people state it in papers. But if often these are made when the estimate, you have exponential convergence, but the constant in the exponent is not controlled and can be very large. Now, in finite chains, in finite irreducible chains, the basic convergence theorems tells you that you always have exponential convergence. You always exponential ergodicity, just because the chain is finite. So, and you easily. So, the whole name of the game is to get a handle on, say, the parameters of this exponential. Okay, so tau will be the first time where the chains meet, and if the coupling is Markovian, which is the only case we consider, so the pairs, not just each chain is Markov, but the pairs also are evolving as a Markov chain, and then we can continue the chain by defining it xt equals yt for t after the meeting time. Okay, so the coupling in this case is going to be very simple. We're just going to run the coupling I described, and the first time the chains meet, we continue them together. So we just have to estimate this coupling time. So before doing that, let's look at the general relation of coupling and total variation. So the probability that tau is bigger than t is exactly the probability that xt is not equal to yt, which is bigger than the total variation distance of these two distributions. So So it follows that if there is a coupling remember that the total variation distance between pt and pi is at most the maximum of the total variation distance between ptx dot and pty dot. So if for every two initial states I have a coupling with then we can bound d of t, our maximal total variation distance, by the maximum over all pairs xy of the probability that the coupling time is bigger than t. Okay, this is a very simple and classical inequality, but in fact it was David Aldous who realized how powerful this method is. Although the idea of coupling goes back to Dublin in the 30s. Okay. Now, if we look at the clockwise, so let's go back to the example of the cycle and the coupling I described to you, and let's look at the clockwise difference between the two particles. So we go from, say, from x to y in the clockwise direction. Then this clockwise difference is going to go up or down equally likely, and when it reaches either 0 or n, it stops. So it's just a walk on in the interval 0, n, which is absorbing at the endpoints. Okay, so again, what I'm looking at is I'm looking at this cycle. I have two marked particles, x and y. I look at the clockwise distance from x to y and see how it changes. So no matter who moves, x or y, this clockwise difference is going to either go up or down, equally likely by plus or minus 1. But the moment it reaches either 0 or n, it stops, because this means that x and y have collided. So this clockwise difference is just doing a random walk on the segment. We start at some distance. Start at some number r, which is the initial distance of x and y. In this clockwise, so this is the clockwise distance. It's not really a metric. And starting from r, we wait till we reach 0 or n. So this is a classical problem to understand the expectation of the stopping time. So if this is r, then the expectation of the stopping time. So this is starting from r. We stop when we reach 0 or n, and this is going to be r times n minus r. Who remembers how to prove this formula? Martingale? So, right, let's. Right, we're just running simple random walk, and so if you use the fact that ER of S tau equals R, and ER of S, what's most relevant is that S tau squared minus tau is going to be a martingale. So just say S tau squared. Or rather, st squared minus t is a martingale. So you can use that to prove this formula, or you can use recursion. Anyway, so from this formula, you see that the expectation is at most n squared over 4.
You just choose xy fixed to.
For any, right, you choose xy are arbitrary because we have to maximize over the choice of xy. But for any xy, the expectation of tau is at most n squared over 4. The maximum is when they are antipodal. And so just from Markov's inequality, we get an estimate. The probability is at most n squared over 4t. And so if we want to relate this to a geometric random variable, we can, once we've done this calculation to an explicit geometric, we could say as follows. Since the expectation is n squared over 4, I have some estimate here. One can improve this estimate always to an exponential estimate if you want, by just saying, if I run for time which is twice the expectation, so n squared over 2, then I know that the probability, just from Markov inequality, the probability that tau is bigger than twice its expectation is at most a half. So I can define a success if tau is less than twice its expectation. And now we know that the probability of success is at least a half. And if we have a failure, so if tau is bigger than twice its expectation, we just try again, because we have control for any two starting positions. So we can try to iterate. So we can easily, by comparison to geometric, we can easily get that the probability. So say the expectation of tau is at most, expectation from any two starting points is at most n squared over 4. So the probability that tau is bigger than, say, k times 2 times n squared over 4, let me write it this way, is going to be bounded by 2 to the minus k. So this is just a geometric variable, or you can think of just independent experiments. Each time I weight twice this expectation, with probability half I've coupled. If I'm not, I'm at some new locations, but because we considered worst case locations, we can repeat the experiment again. Each time we couple with probability at least a half. This gives you a comparison to the geometric, which will give you a tighter bound than a direct application of Markov, as I wrote here. However, so this is relevant if we want to get d of t to be very small. If you want d of t to be less than some tiny epsilon, then the answer will take n squared times the log of 1 over epsilon. But if you only care about epsilon, which is a quarter, then this improvement doesn't matter, and that's what I wrote here. So if you take t bigger than n squared, you get the t mix, which was defined with the quarter, is at most n squared. If you want exact dependence on epsilon, you should use this geometric trick that I mentioned here. Right. On the other hand, you see that the cosine function, properly scaled, is a eigenfunction for the walk, and that's why it's easy to see that the relaxation time here is also order n squared. And so in this case, the mixing and relaxation time are the same order. Now suppose we have a d-dimensional torus. So what is that? It's just a product of d cycles, and or you can think of it as a d-dimensional lattice, but you quotient each coordinate mod n. So, so a particle in the torus, in one step, it's going to only move in one coordinate. It will select which of the d coordinates to move, and then move up or down in that coordinate. So we want to give a coupling analysis of the mixing time here, at least to get some bound. And here we have to be a little more clever, because if we just let the particles move independently, say one moves, one stays in place, until they meet by chance, this will take a very long time. It will take like n to the, if we're in d dimensions, d at least 3, it will take them n to the d steps to meet when they're just moving randomly in space. But the real mixing time is much smaller, so we have to use a more clever coupling. And one possibility is suggested here. So select one coordinate at random. If the particles agree in the selected coordinate, move the particles together in that coordinate. Okay? If the particles disagree in the chosen coordinate, you do what we did in the case of the cycle. So you flip a coin to decide which one of them will move, and then that one moves in that coordinate. So each time we've chosen what coordinate to move in, the coordinate we chose is going to be the same for both particles. But we do a different thing according to have the particles met in that coordinate or not. If they have, they move together. If they have not, then only one moves, and the other one stays in place. Okay, so here is an example. We have the two particles, x and y. These are their coordinates. Here we chose the first coordinate. I'm sorry, we chose the second coordinate. They agree in that coordinate, so they both move in that coordinate in the same way. So both move down from 5 to 4. Okay. Now, in the next step, we choose the last coordinate. They disagree in that coordinate. So now we toss a coin, and x won the coin toss. So x is going to move, and this 9 moved to an 8. The 2 in y stayed in place. Okay? They are doing exactly, but you're right to question this. You know, my grandmother used to say, "Why should I be surprised when I can just disbelieve?" So you should always be skeptical. But yeah, in this case, it does work. So right, so the rules here of how x and y are moving depend on looking at both of them. But if we look just what happens to x, then you can see that in both of these possibilities, x is going to make a lazy move. So when I say they move to, if the two agree, then I say they move together. But then move together here means a lazy move. So with probability half, they stay in place. So a move over our Markov chain is lazy walk on the torus. So you can check that whether x and y agree in that coordinate or not. In both cases, x itself is just doing a lazy move. Okay, so so the expected time to couple the ith coordinate is going to be d times n squared over 4 at most, because it's the same story as before in the cycle, except that that coordinate only gets to move with probability 1 over d. So we have a delay. What before we had expected time to couple we had just one coordinate, and we had n squared over 4. Now it's the same story, but that coordinate is only moving 1 over d of the time. So if you want from formally, you can think of this as an application of Wald's lemma. Wald's lemma tells you that if I'm summing independent IID variables, and let me remind you of Wald's lemma. This is very intuitive, but so Wald's lemma tells you that if xi are IID and t is a stopping time, then the expectation is just the expectation of t, expectation of t times the expectation of x1. So here, if I'm looking at one coordinate, say the seventh coordinate, the random variables I'm summing is how long until I choose that coordinate. These are geometric variables with mean d. And the number of these summons I'm taking is how long until in the cycle, when I'm only moving that coordinate, how many steps do I need until I couple. So that random variable, the stopping time, capital T here, is what we handled in the previous discussion. So that will give us the n squared over 4. And the summons all have mean exactly d, because the summons are just the waiting time until I pick again this same coordinate. Okay, so that gives us the dn squared over 4. And now, since they're d coordinates, the expected time for all of them to couple, this is one naive bound, is going to be at most d squared n squared over 4, because I'm looking at the maximum of these variables. I can always bound the maximum by the sum, and this will get this inefficient bound, d squared n squared over 4. So this gives you the right dependence on n. So you see, no matter, so I'm thinking of the dimension d as maybe a large constant. N is going to infinity. And this is the right dependence on n, so it's constant n squared. But the dependence on d is not sharp with this argument. So we were being too lax in the last thing, bounding the maximum by the sum. So maybe one exercise for you to think about, and I'll come back to it, is to improve the dependence on d. I'll give you a hint. Instead of d squared, what is needed there is d log d. So that's the correct dependence on d. Well, d log d reminds us of coupon collector, but how do you employ the coupon collector to do it here?
The first d is already there. And then
What?
you improve it.
Right. So Exactly. So if I'm looking for the coupling, certainly I need to couple in the first coordinate. So just if that's to couple in the first coordinate is going to take me now dn squared over 4. So that's clearly, or that's clearly a lower bound, dn squared over 4. But of course, I need to couple in all coordinates. So this argument said a crude upper bound, saying, well, I have a maximum of random variables. I can always bound a maximum of positive variables by their sum, and then I can easily compute the expectation. But this is too generous. So you may want to think how to improve that. So it is kind of the same nature as coupon collector bounds, but I don't see, an exact deduction from the coupon collector. So it's actually more related to Krishna's question earlier about geometric, how we relate this to geometric variables. Anyway, I think it's good for everyone who's not seen this to, think a little bit on their own about this, and then I promise I'll share the argument with you later. And
relation between mixing time and the coupling time is coming from the super variation distance, total variation distance.
Right. So this I emphasize. I explained this before, and this explanation was not. This is the proof here. It's completely general. Okay. I can't hear if. Yes. Right. Yes, all these things have, can be done with looking at moment generating functions. Yes. So the argument, this kind of elementary repeated experience argument can be replaced by argument with, on the moment generating function, and that can work. Yeah, that can be done. Okay. I'll come back to this point. Yes. So, yeah, let's see. Okay, so we'll take a break now and continue after.